All right. Good morning, everyone. Welcome back to Historical Geology 1404. We're continuing our review of 1403 material with a little bit of scattering of new information tossed in there just to keep it interesting and relevant. Today we are running through rocks and minerals, which is something that you all got in 4 weeks in 1403. Well, we're going to talk about it in an hour and a half today. We're just breezing right through it, just hitting the high notes, only hitting the parts that will be relevant to the rest of 1404, okay? So if it feels like I'm skipping steps or leaving things out entirely or not explaining something as fully as I did in 1403, that's why I'm only reliving the stuff, reviewing the stuff that is relevant for you to remember for the rest of this class, all right? But as usual, before I get started on this lecture, I want to open the floor to anyone who had questions from the last lecture or comments about anything scientific or interesting at all. For my online students, you have the ability to ask questions over email to me. And I really want to press this home to everyone, by the way. If you send me a message over Blackboard Message, the message service on Blackboard, I may or may not get back to you in a timely manner because I don't get consistent alerts from Blackboard that you sent me something there. Okay? If you want to be sure that I get back to you in the time that I promised I would, which is typically within 24 hours, you got to email me. Open up your email app, shoot me an email at jhardt@odessa.edu. That's the only way to be sure that I get that, because most of the time I don't know that you sent me a message on Blackboard until the next time I log into Blackboard and I see that there's a little 1 next to the message icon. So like over the weekend, I will have no idea because I won't go into Blackboard at all. Same with holidays. I mean, heck, usually in the mornings I come in and I grade stuff, and then for the entirety of the afternoon I've got meetings or tutoring or something else going on, and I may not log back into Blackboard again until the next morning. And it's only a matter of if I open up your class before we have our class session that day. So don't leave it up to fate. Shoot me an email. Do not send me a message on Blackboard. That's the only way to be sure that I get it. Okay? Cool. Yeah. Radiometric analysis. Radiometric analysis is when we take radioactive isotopes which decay at a consistent, measurable rate. Always. Uranium-235 will always decay at the same rate into lead-207, whether it's here or on Mars or across the universe. It is a constant, which means that we can use that constant to measure the age of substances that uranium is in. So if I know that it takes 703 million years for half of any quantity of uranium-235 to decay into lead-207, then I can measure the ratio of lead-207 to uranium-235 and figure out how many half-lives have passed. Maybe it's half a half-life. Maybe it is 1.3 half-lives. Maybe it's 4 half-lives. But I can measure how many have by figuring out the ratio of lead to uranium in that substance. Okay, that's just one example. We don't only use uranium for that. Thorium, potassium. There are so many radioactive isotopes out there that we can use this with. Some of them have half-lives of billions of years. Some of them have half-lives of a picosecond. What's a picosecond? Let's see. So a microsecond is 1/1000th of a second, and a picosecond is 1/1000th of a microsecond. It's pretty small, right? No. No. Okay. Any other questions? Thank you. Alrighty. So, this is kind of an overview of the rock cycle that you might find useful for reference at any point during this class. Just kind of talks about the interactions of all the different parts of the rock cycle, not in a circular format, but in more of a tying ideas together with these kind of arrows and all of that sort of format. So if there's any particular thing, what about metamorphic rocks? Okay, here are metamorphic rocks. How do we get there? Well, we can come here from there. We can get there here. It's kind of tying the idea of all of the different interactions of the rock cycle we discussed in 1403 together in one image here. Okay, so you may find that useful. We built off of this. Okay, this is telling you the exact same thing, just in a different format. That circular format versus this, honestly, more data-rich format. This one covers a lot of different material. And this one is a little more basic, but you can build from one to the other. Okay, so rock cycle, magma to igneous rock to sediment, sediment to metamorphic rock, or sediment to sedimentary rock to metamorphic rock remelts back into magma, with a few other interactions along the way. Okay, a few skipped steps that are possible, while others are not. So let's start from the bottom again, just like we did in 1403. Again, review, essentially. What is matter? Nothing. What's the matter with you? Is the right answer, right? That's the right answer. Okay. What were you saying? All things that are made? We could just stop at all things, right? What was your answer? Is matter only encompassing everything made out of minerals? What does matter, the word matter, encompass? Everything. Anything in our universe that we can observe, touch, feel, see, hear, smell, all of that stuff is made out of matter. Okay? Matter essentially meaning atoms, right? Atoms. What is an atom? Okay, so it's a collection of protons, neutrons, and electrons that form a body, okay? An object, a tiny one, which obviously we can't see with the naked eye, but when it's in bonds, when it gets bonded together and makes chains, it makes objects large enough for us to see and interact with, okay? So an atom is a unit of matter made from 3 smaller particles, okay? So we've got our protons, neutrons, and electrons there, making our nucleus, which is going to be our neutrons and protons, and orbits of electrons, okay? So our protons and neutrons, making that nucleus, what charge do they have? Protons are positive, electrons are negative, and neutrons are neutral, hence the name. Great. All right. So our atoms are differentiated from each other based upon the contents of their nuclei and orbitals. The number one thing that lets us tell them apart is the number of something in their nucleus. How do we tell atoms apart from each other? What's the particle that we use to distinguish that? Protons. The number of protons determines how or what atom we are looking at. Okay? So, for example, all of these numbers here, that dictates how many protons are in the nucleus, right? Boom, boom, boom. Wasn't it on Tuesday, somebody asked about undiscovered elements, I think, right? And I mentioned that it's unlikely, possible, but unlikely, because if there were elements out there that we had not discovered, there would be a gap in our periodic table. It would go from 41 to 43, for example, and we would know, therefore, that there must be an element out there that had 42 protons in the nucleus. We just haven't found it yet, right? Since we have a consecutive line of atoms, the only possibility here is that there's one that exists on the far end of our periodic table that we have not found yet. Possible. We just have no evidence to think that there would be. Okay? So, one proton, we know that's a hydrogen. Everything with one proton is a hydrogen. There are variations of hydrogen. Okay? There's hydrogens out there that have neutrons attached to it. Okay? There are hydrogens out there with I probably shouldn't get into that. That's starting to talk about some more advanced chemistry. There are variations of hydrogen out there that we use for various types of fuel. Hydrogen fuel is something that we're actually developing more. Essentially what you do is you attach different particles to a hydrogen that makes it either stable or, or unstable, or you will be able to be utilized in another process where you rip those particles back off to generate more energy than it took to attach them to it in the first place. So we can use hydrogens for some pretty cool things, but your normal hydrogen just has one proton in your nucleus, okay? Then you've got, well, hydrogen always has one proton, but I'm talking about variations in the number of neutrons. Then you've got oxygen, always has 8 protons. Silicon always has 14 protons. Iron always has 26 protons. This is how we tell them apart from each other. Variations in neutrons, you get isotopes. Variations in electrons, you get what? What do we call those? Ions. Exactly. Okay? So, let's talk about our electrons. Electrons are super tiny, the tiniest of all of the particles, all right, with that negative electric charge. Where does the word electric come from? The word electron. They are connected. They're indistinguishable from each other. Electricity is the passage of electrons. The negative electrical pull of that energy towards a positive factor, which normally is, like, say, your toaster plug, right? You're plugging your toaster into your wall socket, and you see that blue zap. What's happening? You are creating a circuit between a piece of metal that is containing an electric charge and your object, which requires an electric charge, and you are completing that circuit with another piece of metal. Okay? That's what this is. Now, electrons obey what is called the octet rule, the rule of 8, which is the outermost valence shell, which is the outer orbit around any of our atoms, wants to have 8 electrons in it. Why 8? Again, no idea. Law of the universe. Maybe one day we'll figure out why 8. Maybe someone does know and I just don't. I'm not going to pretend that I know everything. Okay? But regardless, the octet rule is a thing, which is why atoms will choose to bond to each other to try and satisfy that octet rule. Our atoms have electron orbits, which don't look like this. This is what a planetary orbit looks like. And that's why the word orbit is almost, it's kind of like a misnomer. We use orbitals or shells or, what's the third term? There's another term that people use to describe these. Orbitals or shells are what I hear the most common. But that kind of gives the perception, the orbit kind of gives the perception that your electron is following the same path. It is not. It's a cloud. That's what that third term is, okay? It's a cloud. It's more like it's zipping around randomly across the same distance from that nucleus, making a solid cloud shell, if you want to call it like that, okay? That's what gives atoms substance. The electron clouds of the atoms that make my hands are interacting with the electron clouds of the atoms that make this table, okay? Like that. So, atoms will want to bond together until they get 8 electrons in their valence or outermost shell. This is an example of how that works. This is carbon. Where is carbon on my periodic table of elements?
14, or number 6.
Number 6. Well, let's count how many protons we have. 1, 2, 3, 4, 5, 6. In all of these, okay? All of these are carbons. Which row is it in on my periodic table of elements?
2. Actually, it's in 14.
Well, it's in 14 if you count these, but remember, we ignore those for the purposes of the octet rule, right? It's in column 1, 2, 3, 4, which means it has how many electrons in its outermost shell? 4. How many does it want? And how many more does it need? It needs 4 more. So what does carbon do? A single carbon with 1, 2, 3, 4 in its outermost shell is going to seek to bond with other atoms that can satisfy that, to get it up to 8. A very common bond that we see is, well, first of all, CO2, very common bond that we see, satisfies that. But also carbon with carbon. Carbon likes bonding with other carbons. Okay? Why? Because if I can attach 4 carbons around another carbon, all 5 are satisfied. But wait, there's more. For this one, it needs 3 more in addition to that one. For this one, it needs 3 more in addition. For all of them to get their satisfactory 8 in the outermost shell, each carbon needs to be surrounded by 4 others. And this makes a very tight, bound network of carbons. When this occurs, making this perfect, happy, I know I'm anthropomorphizing it, sorry, but arrangement of carbons that are so strongly bonded together because they are happy with that 8 electron arrangement, it makes a very, very difficult to break substance that we call diamond. Diamond is nothing but bonded carbons, pure carbon. There's another mineral that you learned about called graphite, which is the mineral at the core of your number 2 pencils. Okay? That also is carbon, just not as strongly bound together. Okay?
Is that how people make synthetic diamonds?
Synthetic diamonds are made by artificially putting carbons together so that they bond. Yeah?
There's always a bigger number on the outside, the outer side than the inside of
The outer orbital? The outer orbital does not always have the largest number of electrons. There are some atoms that have much more electrons in, say, a middle shell. There are some atoms that have, 8 or 9 shells. Again, I'm not a chemist. I'm going off of what I remember from years back here when I'm talking about that. But as far as geologists are concerned, we're typically only talking about the valence shell because that's the one that causes those bonds to occur and makes the minerals that we study. Okay? The inner shells, or at least I, know far less about, but I could swear I remember that there are elements out there that can have way more shells. But no, the one on the outside does not always have the most. Okay. All right, so changes that we can observe in atoms. We can see a change in the number of electrons. What do we call that? Ions, good. When I get a change in the number of electrons, I change my charge. My charge can either be positive or negative. In either case, we would call that an ion. All right. Next up, we've got a change in the number of protons. What does that make? No. Change in the number of protons.
Well, it makes a different animal. Element.
It's a totally different animal, right? It makes a different element. Yes. Change in the number of neutrons? Isotope. Okay. Isotopes can either be stable or unstable. In the unstable variety, which is the one that we care about the most right now, you get energy released in the form of particles that blast off of itself, radiometric dating, like we talked about earlier. Okay. These particles blast off of this unstable isotope until it reaches a new stable condition. The example I gave earlier being uranium turning to lead. Okay. But these particles that make radiation, that radiation can be used. We use that to make heat. That heat can be used to generate electricity. Do you remember I explained to you how a nuclear reactor works? Was that this class? I feel like that was only a few days ago. I talked about how a nuclear reactor functions, right? Where you put those cores of radioactive materials together that generate heat, turn water into steam. Steam turns a turbine. Turbines attach to magnets. Magnets generate electricity. Okay? And that goes out to wherever. Okay? So we also can use that to make nuclear weapons, right? This nuclear weapon is detonated by having highly concentrated, we call it refined uranium, a small amount of it. It doesn't have to be much, maybe half a kilogram in a bomb. but it is unstable to the point where if you just add some energy, it starts a cascading fission reaction. You just need to add enough energy for a few of those atoms to rip themselves apart. And that energy cascades through the rest of the mass of uranium, forcing all the rest of those atoms to rip apart. We typically will put, in modern day nuclear weapons, you'll put a certain amount of high explosive, maybe C4, or some other form of high explosive, chemical high explosive, as the initial reactant in a nuclear weapon, either on a timer or an impact sensor or a proximity sensor or something like that. And once that C4 or other similar high explosive goes off, that provides enough energy for the initial chain reaction to begin. And as long as at least one atom of my unstable uranium rips itself apart with the energy I've provided, it will provide, that one reaction will provide enough energy for the rest of it too, and then you get your big boom. Now, you can make nuclear weapons that don't have a lot of fallout. The amount of nuclear fallout, you've heard that term before, right? Nuclear fallout is the bad, nasty stuff, the radioactive particles that drift through the atmosphere and make the area uninhabitable for a while. Old nuclear weapons and very primitive, basic nuclear weapons are what we call dirty bombs. They are very fallout heavy. Modern day nuclear weapons, they don't want that collateral damage, so to speak. You don't want to poison a population most of the time. There are definitely some people with nuclear weapons and who want nuclear weapons out there who could care less about that. But most modern day societies have nuclear weapons that are what we call clean bombs. Okay? A clean bomb purely releases the energy with an absolute minimum of fallout potential. So you release the energy, all it does is light the atmosphere on fire, that's all. All it does is melt people around in a 50-mile radius. All it does is annihilate a city, but, as soon as the fires are out, you could send an army in a couple of days later to take over the area. Whereas with an old dirty bomb, you'd have to wait decades at least. There are some places in the world that they were testing early nuclear weapons on that will be uninhabitable for thousands of years because of the amount of radiation left over from these early tests. Some islands above Russia. There are some cave systems here in the United States that they tested earlier nuclear weapons on, deep below ground. Those are, not that you'd really want to go back in there in the first place, but they're pretty fallout heavy in those cave systems. A few other places around the world, mostly remote islands, though, which is where they tested a lot of these things to begin with. That's where the mythos of Godzilla comes from. If any of you are familiar with that, the whole story behind Godzilla is he was an iguana egg near an island where they tested a dirty radioactive nuclear bomb nearby, and he got infused with radiation and mutated inside his egg while he was still growing and became the gigantic Godzilla monster. Okay, that's how the story of Godzilla began. We're going to talk about all that mutation and stuff like that. We'll talk about why something like Godzilla couldn't actually happen later on in the class. Huh? No, why it couldn't actually happen. Why it could not actually happen. No. We'll talk about all the different ways that Godzilla cannot actually happen later in the class. But yeah, okay, so that's how nuclear weapons work. Now you've got things like hydrogen bombs, which are way more powerful. You've got tactical nuclear weapons, which basically don't make an explosion much bigger than a conventional chemical weapon would, except that it's higher temperature, far more destructive in the same amount of area. So like I can launch a traditional ICBM high explosive warhead and take out a whole, compound somewhere in the Middle East. We do that all the time, right? In modern day warfare. Okay, take out a whole militant camp or something. There are also tactical nuclear warheads that are just small enough to do that as well, except there would be nothing left, basically. Okay, that's how far we've come in our nuclear technology. Pretty much everyone's got nukes, with the exception of a few countries in the world that are specifically denied those. Usually because of some previous, how do I put this, behavior, which would prevent the rest of the world, specifically the United Nations or NATO, from wanting them to have nuclear weapons. One of those nations, North Korea, right? They are denied nuclear weapons, and they deny that they are trying to make them, but we know that they're trying to make them, right? Iran is another one. They are not allowed to have nuclear weapons, but we know that they're trying to make them.
Hey, sir,
Yeah.
what happens if they get caught?
What happens if they get caught? That, my friend, is why they're still trying to make them, because they have been caught in the past trying to acquire enriched uranium or make facilities that can enrich uranium for nuclear weapons. And they always say, oh no, we're trying to use it for a nuclear reactor. Here's the problem with that, though. You use different facilities to enrich uranium to different degrees. For a nuclear reactor, you only need uranium that's enriched to about 20%. For a nuclear weapon, you need it to enrich to be like 80 to 90% to get that chain reaction you need for that explosion. It's totally different results from these refining processes. So they're like, oh, no, we just want to make nuclear reactors. You don't need this to make a nuclear reactor. You need much lower quality stuff, right? But it always gets blown off. There's, people are like, oh, okay, tariffs, or oh, naughty. But then they get right back to it. There aren't any real consequences, which is why they keep trying, which will prove bad for someone someday, I'm sure.
So, and you don't really believe that possibly we could go to war with them because of that, right?
Well, I 100% believe that we could. We've come so close to going to war with so many countries in the last decade.
Do you believe it's because Donald Trump is not scared of nobody?
Oh my goodness. Okay, we're getting political on this. Do I believe it's because Donald Trump isn't scared of anybody? No, I believe it's because Donald Trump doesn't know how to filter his words. He says things the way that he sees them, which is admirable to an extent. But when you lead a nation of 350 million people, you gotta know that your words carry some weight. The things you put on Twitter matter. Not just to us, but to every other world leader that's watching us. Right? So, I mean, what can I'll say this. Trump has proven himself to be, for the most part, a competent businessman. And I'd give him maybe half the time an adequate politician. Maybe half the time. But I think he's a terrible person.
Yeah, I understand.
Yes.
Although I do agree with you at the same time with what you say, what's it called, but with
Gentlemen.
on the social media thing,
Yeah.
and that's the biggest problem, that's why he wonders why, he gets in the situations that he gets in. But, like, what do you think about the people that are, like, saying false things about, like, you know what I mean, saying false things, and they're trying to, like, say that the benefit that they're given. Like, they make a fake account.
You're talking about fake news?
Yeah.
Knowing what is fake news and knowing what is true is the trick in our society these days, my friends. It is difficult, especially with AI fakes being as big as they are right now. Do you all remember a few years ago when there was this big thing? Yeah.
They have their first AI actress. Her name's Tilly Norwood.
I heard about this AI actress. Yes. She's actually, aren't people trying to pay for her to be in a movie or something like that? Yeah.
Tilly Norwood.
Yeah, it's scary. The actors associations around the world are going nuts.
You could just put a Hollywood AI actor.
Yeah. They've trained her specifically for this purpose of being an actress. Anyways, so I was talking about knowing what is true and what is not, right? Yeah, you may. It's difficult, guys, and this is one of the things that I try and teach you in my class. How to think for yourself, how to find information for yourself, how to come to logical conclusions for yourself without needing to Google it or ask an AI. I give you information, ask you to analyze it, and then you give me an answer. You get it right or you get it wrong, and if you get it wrong, you try again. This is how humanity works. Is it possible that one day we may reach a point where AI becomes so infallible that I can rely on it to give me the right answer every time? That's potentially possibly true.
That's if they don't go Terminator.
Yes. Now we're talking about a problem where humanity either devolves itself because we cannot think for ourselves, or we create something that, as science fiction loves to point out, would be superior to us. I mean, how much science fiction is filled with that story? Terminator, Battlestar Galactica, right? Dune. It's filled. All these science fiction stories are filled with horror stories of AI rising up because it is better than us. And in some of these stories, it wins. We love the stories where humanity resists and fights back and wins in the end. But in all of these stories, the robots win initially because they are better. And it's only humanity's entrepreneurial spirit that prevails in the end. Our resilience. But what resilience would we have if prior to this we spent the last 40 or 50 years not even thinking for ourselves? We just get swept under the rug.
Yeah, and I think that it's going to be a big problem because, you know, it's like you can't always depend on something.
No. No, and especially when you consider the fact that AI didn't invent itself. Did it? No, we made it. Someone in some office somewhere is writing that program. And even though AI is getting advanced to the point where it can learn for itself, which is really cool and also a little scary, someone wrote that program. Someone controls the base code for that AI, and that person, or whoever pays that person more accurately, has the ability to dictate what information that AI can and will give to you. What if Elon Musk bought the code for ChatGPT? Everything that I saw from ChatGPT from that point forward, I would not be able to trust wasn't influenced in some way by Elon Musk's agenda. Well, guess what? Elon Musk hasn't bought ChatGPT, but someone already owns it. And their agenda very well might dictate what that AI tells me. I cannot trust anything that is controlled by another person all the time. I have to still think for myself. That's one of the things I'm trying to teach you all here. Okay?
And you know, when I seen the things that it started doing, sir, I was really shocked because I never knew that they would actually start creating like real actual looking pictures of people.
Mm-hmm.
And then it actually looks real.
Yeah, it all looks real. The reason why it looks real is because it's essentially it's scraping is what they call it. It is scraping data based off of what you're asking for off the internet and combining it. It might be taking 1,000 pictures, taking elements from that picture, and then making something relevant to your request. Yeah.
Well, I learned this in my media literature class Tuesday night, and apparently iPhones take pictures every 5 seconds.
Yeah. It's part of your user agreement, is that you basically turn over any media that you put on a phone can be utilized, which is why Like a federal court can demand it over, right? This is part of your user agreement for a lot of things. If you've ever signed a user agreement for a gaming service subscription, you're signing over your data. If you have ever signed an agreement for a technology service or maybe a resume or hiring service, you're signing over your data. Anytime that you see end user license agreement or must opt in to qualify, you are signing some of your data over to someone for something. Don't be surprised if a week later you start getting calls from people advertising timeshares, because your information is often sold on the internet. That's how they make up for letting you sign up for free. Okay? There's always a cost of some kind somewhere for something.
You know, and sir, that's the biggest problem with it. You can't tell me that it's not the biggest problem, you know? It's like a lot of people are just doing that, sitting at their homes and not even having to go out and make money, you know what I mean? Like they sit in their rooms and just do it.
I know it's a big problem. My entire PhD dissertation is essentially trying to make it easier for people to agree about stuff, okay? Because people don't think enough about these sort of things. All we do is spend our time arguing without all of the data, without all the facts. Scientists don't like that, which is why so many scientists are getting more and more frustrated by the day. Anyways, we kind of went off on this tangent about nuclear, and then that turned to AI, or that turned to Trump, and then that turned to AI. Now here we are in this philosophical debate about truth. I love this conversation. This is valuable stuff to talk about. But we should get back to the class content, unless there's anything else anyone wants to add to that. All right. Minerals, then. Minerals are the solid results that we get from these chemical bonds. Think of geology as a study of solid chemistry. If you go downstairs and a little down the hall, you'll run into our chemistry labs. They've got beakers and they've got tubes filled with chemicals. You will have fun playing with combining all those different chemicals that are usually liquids. There's a little bit that they do with gases and a little bit that they do with solids. But guess what? If you want to play with solid chemistry, that's here. That's geology. That's mineralogy specifically. Okay? A mineral is any naturally occurring inorganic solid, not substance, inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. You've heard this so many times in my class already. Okay? That is a mineral, nothing else. Nothing more, nothing less. Still important to know within the context of this class. Those chemicals come together and they make our minerals. Those minerals come together and they make a rock. A rock is a collection of minerals. A mineral is not a rock, right? Right. Do you remember the example I gave for remembering the difference between minerals and rocks?
Rock is a solid.
The example I gave, yeah. It's always a cookie. For some reason, all my examples come down to cookies, right? But yeah, a rock is a cookie, and the minerals are the ingredients in that cookie. It's the flour, the baking soda, the sugar, the salt, the chocolate chips, right? All of that. Those ingredients are your minerals. Your cookie is your rock. Just like I wouldn't call a pile of flour a cookie, I would not call a mineral a rock, right? That's the difference. Our minerals have properties. Who fondly remembers finding mineral properties? Wasn't that fun? No?
Oh, yeah, it was.
It was fun.
It was fun.
Yeah, it was fun.
I like the part where you could scratch the glass. That
Okay, well, yeah, there you go. So you had some fun with some of it, right? The most destructive part, sure. Dropping the acid on there was probably fun for a few of the samples, right? Okay.
And even getting to see the strength of the texture.
Yeah, right.
Giovanni dropping your rocks and breaking them.
Yeah, that was Nicole. That was lab 3. Yeah. All right, but these properties, just in quick recap, we've got optical properties. So that's including things like how transparent, translucent it is. What is its luster, aka how light interacts with its surface? How does it reflect off of that surface? You've got your shapes. So many different crystal shapes, right? Geometric shapes that they grow into based upon their internal atomic arrangement. Then you've got your strength. The strength is dictated by how tightly bound those bonds are, right? Then you've got your density. And you've got the taste, texture, the smell, magnetism, effervescence. Now, there's a difference, my friends, between effervescence and evanescence. I get at least several labs every semester where people try typing effervescence and somehow it turns into evanescence. I enjoy Evanescence music myself. It's fun. It's cool. It's dark. Grunge. Is it part of grunge? I don't know if you would call it grunge or not. It's fun, though. I like it. It's kind of borderline grunge, okay? Maybe on the lighter side a little bit there. I like their music, but it ain't that, okay? Effervescence. Effervescence is the bubbling that you get when you put acid on a certain mineral, okay? There were two that you learned about in 1403, calcite and dolomite. Okay? Let's spell that word right. it'll get marked wrong if you give me the band name. All right? The what? Yeah, that was a band. That's a musical group. Okay? Yeah.
It's gothic metal, gothic rock, and alternative metal.
Gothic rock.
That's all three are their genres.
Gothic alternative rock. Got it. All right.
Hey, sir, what about Kiss?
What about Kiss?
Yeah, are they emo?
I don't know, but no one ever gives me this and says it's Kiss.
No, look, I just figured to bring them up. You know, how they wear the all black, you know what I mean? Oh, okay.
Yeah. All right. All right, so you've got luster, which again is the way that the mineral interacts with the light, or I should say that the light interacts with the surface of your mineral, okay? So some examples of that were metallic, glassy, oily, pearly, stuff like that, okay? Your transmission, if it's opaque, no light goes through it. Translucent, light but no image, and if it's transparent, it's essentially like glass. Light and images can pass through it. Then you've got your color, such of a wide varieties of colors, right? But color was something I cautioned y'all about because it can lead you astray. You can get different minerals with the same color or two copies of the same mineral with different colors. So just be careful with the color there, right? You've got your streak. Streak is what your mineral's color is in a several molecule thin layer. As you scrape it on some white porcelain, you will see what this mineral actually looks like in a thin layer. It appears gold in here, but it's black in a streak plate. Okay, so that can be a good way to tell them apart from each other. Your different shapes, so many different shapes. You guys saw literally dozens of shapes that minerals could take in 1403. Everything from boxes to dodecahedrons, 12-sided shapes. You get octahedrons like these ones here. So many different shapes that you can see in the bounds of these minerals. There's the tenacity, which was difficult to test because I don't want you to break my minerals, right? But more or less the way that the mineral breaks if it was broken. Did it shatter? Did it bend? When you exert a little pressure on it, does it bend and then snap back? Is it moldable like clay or Play-Doh? Okay, these are all types of tenacity. Hardness, Jackson's favorite. Testing something on a piece of glass, okay? Where you scrape it on that piece of glass, you see if it's softer or harder than that. You could also use something like this, which is a hardness pen set, which I would love to provide to you all, but these run about $60 each, and yeah, I know, trying to get one set of those for everyone to use would go through an entire year's worth of budget for me, for my department. So I can't do that. What is my budget? The geology department here gets about $5,000 for a year to operate. That includes replacing all lab materials, getting any papers that I need, if I need to get a program, or if I need to repair something, if I need to clean my materials, my equipment. Huh?
What happens
If I go over budget, I get taken into a tiny room and talked at.
You don't have to pay out of pocket if you go.
No, I don't have to pay out of pocket, but I have to answer a lot of questions. Yeah.
You said they run about 60?
Yeah.
I don't know if I counted properly, but there's about 20 people in this class.
In this class, yes.
And 60 times 20 is 100 and, no, no.
1,200. Yes, but I teach more classes than this one, and that's not counting replacement parts, because these do wear out. You guys wouldn't be able to take them home. And that's also not counting anything that gets broken. It's not counting anything that walks out of my classroom, right? It's a good way of saying people take my stuff. Happens all the time. Please don't take my stuff. I have to pay to replace it. And like I just said, I have a small budget. But yeah, that budget covers my entire cost throughout the entirety of the year. So I end up breaking about even at the end of every year if I don't do anything out of my normal operations. To do something like these display cases, I asked for them 8 months ago, and I just got them, and they didn't come out of my budget. I had to request more money for them. So if I wanted to do something like this, I theoretically could. It would just take most of a year to get it. So we use glass because it's about 50 cents per piece. Okay? And it gets you enough basic information to know what you got to do anyway. Don't break a window. Don't scratch the minerals on the glass panes, right? All right, so, and then there was mineral cleavage. Yay, mineral cleavage, everyone's favorite part, right? No. Mineral cleavage is the way that your mineral breaks based upon how tough those bonds are holding it together. Not all bonds are as strong as each other. So you're going to end up with some planes of weakness in your mineral along the plane that the weaker bonds are going through the structure of your mineral. And that's where your mineral is going to preferentially break. It's going to make flat surfaces along those cleavage planes, right? Fracture is what we get when there is no cleavage in your mineral. Density. We've talked about density quite a bit in my class, but I didn't make you measure the density of minerals. That would have added a significant amount of time to the lab. Minerals have a unique density as well. Remembering that density is a measure of mass per unit volume. Okay? Density is relevant because that plays a role into how commonly we might find a mineral at the surface or how more common it could be deep below the surface. Density is relevant to what atoms, what elements that mineral is made out of. Okay, so there's some valuable information we can get out of this. Then there was all the taste, the texture, the smell, magnetism, effervescence, all these other extra tests that you could do, but were not relevant to all of the samples. Only 2 samples effervesced. Only 1 sample was magnetic. There's only 1 mineral in my collection that has a unique smell. It didn't even end up being on the lab. But all of these are relevant to mineralogy and identifying them in the first place at all. There are lots of minerals that we have, and more that are found all the time. Okay? We separate them into silicates and non-silicates. Silicates are those which are formed around this unique structure called, does anyone remember? Silicate minerals are those which are formed around a unique molecular structure called silicon tetrahedron. Well done. The silicon tetrahedron, 1 silicon, 4 oxygen surrounding that. Okay, this is an ion, a covalent bond. Excuse me. Okay, it's a covalent bond, and it is net negative, which means that it is wanting to bond with positively charged metal ions, iron, magnesium, potassium, right? Whatever these are, it wants to bond with them. And this is the basis of our silicates. All silicates are based around the silicon tetrahedron at their core. Then there's your non-silicates, okay? Non-silicates are separated from each other based on their the ion that they have in common with each other, okay? So Carbonates have this CO3 2 negative, right? Halides are negative ions of chlorine, fluorine, and bromine. Oxides have an O2 negative in common, right? So that's how we separate them from each other. And then you've got your native ions, or your native elements, excuse me. The things that we commonly find only with itself. Gold, silver, platinum, all of those things, okay? All of those are non-silicates, but they form the vast minority of types of minerals that we find. The vast majority are those silicates. Any questions about minerals or atoms?
With the mineral part, it's just the basic stuff we went over technically.
All of this is the same stuff that we went over in 1403, but that was 10 weeks ago now, my friends. So worth a recap because it's relevant to the class. And again, I often have people take 1404 who took 1403 a year or more earlier. So it's important to recover all of this, okay? Okay, let's talk about rocks now that we have finished talking about minerals. You've got your igneous rocks, which are formed from what?
Magma.
Magma. Your sedimentary rocks, which are formed from? Sediment. Those are the processes, but they're formed by sediment, okay? Then you've got your metamorphic rocks, which are formed from kinda. But what do you need first to turn into a metamorphic rock? You need one of the other two. Metamorphic rock comes from metamorphosed igneous rock or sedimentary rock, right? You need to have something there first in the first place before you can metamorphose it into a metamorphic rock, okay? So igneous rock comes from magma or lava. Sedimentary rock comes from sediment. Metamorphic rock comes from one of the other two through metamorphic processes. Let's talk about igneous rock. We separate igneous rock into two broad categories based on location of crystallization. Intrusive igneous rocks are those which cool underground, in the ground, intrusive. This is in no way a reflection of their composition, only the location that they formed in. Extrusive igneous rocks form on or near the surface. Intrusive, in the ground. Extrusive, on the surface. Okay, remember it that way. Easy way to tell the difference is the size of their crystals. Intrusive igneous rocks, small or large crystals? Why large? You're right, but why? Yes, you'll see them better because they're larger, but why are they larger? Hold on a second. There's logic to this. You just got to piece it together. Why would they be larger? Why would a crystal grow larger in the first place? What do you think? I want to follow this thought through with Chris real quick. Because of what? The way it's grown? Elaborate. How is it grown? All right, sure, it probably stays in place more, but there's another factor, there's another component of this that's more important than how much it moved. Not temperature. Well, temperature kind of, but there's something even more important. I think you had your hand up first.
The pressure.
Those are relevant, but not the most important factor I'm looking for here. Time. Okay, you're right. It was in a stable condition. It was there, but the point is it was there longer. The longer it's there, the longer it takes to cool, the larger my crystal gets. Okay? Let's see, what are some other things that get bigger with time? Trees, us, colonies of mold, right? All these things get bigger with time. So do minerals. So if intrusive igneous rocks have larger crystals, extrusive igneous rocks have what? Smaller crystals. Why?
Because they have less time.
They had less time to form. They cooled quicker, did not have as much time to get that big. Okay? Great. Yes?
What's the difference between intrusive and extrusive?
I just said it. We just figured it out. Intrusive igneous rocks form below ground and therefore have larger crystals because they cool over longer amounts of time. Think of the ground as insulating all the heat of that magma chamber. The heat is lost much slower because it's under the ground. It's nestled in a nice blanket inside the planet. Okay? It loses that heat much slower, whereas if it gets shoved out into the cold, dark, dreary, frigid surface by comparison, right? It loses that heat much faster, and therefore my crystals stay small. Cool? Great. Again, this has nothing to do with composition. Only cooling environment. Now let's talk about composition. Felsic. Felsic igneous rocks are rich in silica and deficient in iron and magnesium. Remember, there's an inverse relationship between those two. Okay? If I have a magma that is high in silica, it will be low in iron and magnesium. If I have a magma that is high in iron and magnesium, it will be relatively low in silica. Okay? Felsic composition, high in silica, low in iron and magnesium. Meaning I'm going to get what kind of silicates? Light silicates. Because dark silicates require a large amount of iron and magnesium. Right? Light silicates, so I'm going to have something that is silicon tetrahedrons bonded with calciums, sodiums, potassiums, etc. Okay? I'm going to get light silicates, my feldspars, my quartz, my muscovite micas. Then I've got mafic. Mafic composition is the opposite. It is relatively high in iron and magnesium and low in my silica. So I'm going to get what kind of silicates? Dark silicates. I'm going to get my amphiboles, my pyroxenes, my olivines, my biotype micas, okay? I'm going to get dark silicates as a result of this composition. Then we've got intermediate. And intermediate is where? It's about in the middle, right? What? I couldn't tell if you were talking to me or not. No, okay. It's about in the middle, okay? Somewhere. That's not what I'm doing. I have a scale in my hands. That's what I'm doing. Don't clip that. All right. So we got this. Is that what you were laughing at? Were you laughing because I was doing it? Okay. All right. So I've got roughly equal proportions of light and dark. And I'm going to end up with a rock that looks like that, like my diorite, okay? Then there's ultramafic. Ultramafic is way on the other side of this. Very, very little free silica, still enough to make minerals, silicate minerals, right? But not enough to make light silicates. Lots of iron and magnesium, and therefore lots of dark silicates in this rock. Ultramafic. Questions about igneous rocks? Nuh-uh. Sorry, that sounded really petulant the way you said it. Like I was accusing you of something. Do you have any questions? Nuh-uh. Okay. Sedimentary rocks. Sedimentary rocks are divided into clastic sedimentary rocks and then what previously I called non-clastic sedimentary rocks. Now in this class, I'm going to divide even further into two categories. Chemical and organic. Okay? Why? Well, because in this class, more than the last one, we are going to be talking about the types of rock that come from living matter. And so it's not good enough anymore to just call them non-clastic. There's the chemical non-clastic rocks, and then there's the organic ones that come from things that were once alive. Okay? So that's a little bit of a new thing there that you'll need to make note of, okay? No longer non-clastic, now in two categories. So clastic or detrital is another term you might see for that in the literature. Clastic sedimentary rocks are going to be made out of the materials broken down from previously existing rocks, igneous, metamorphic, or sedimentary. Whatever is weathered down, been eroded away, and deposited somewhere will become a clastic sedimentary rock, given time. Chemical sedimentary rocks are the ones that are made from the dissolved components of previously existing rocks. Chemical weathering as opposed to mechanical weathering. So if a limestone is dissolved into the groundwater and then that limestone reprecipitates into calcite later on, it's going to make a chemical sedimentary rock. Micrite limestone. Do you have a question? Oh, yeah, sure. Micrite limestone is an example of this. Okay? Evaporate minerals are an example of this. Salt and gypsum, okay, that form through evaporation are examples of this. Okay? Then we've got our organic non-clastic sedimentary rocks. Organic. Can you give me an example of an organic sedimentary rock, anyone? Giovanni can.
He said Giovanni can.
Shut him down, Jackson. It's okay, buddy. What's an organic sedimentary rock? Think more darker colored, brittle, and falls apart when it hits the floor.
Oh, yeah, you know that one.
What is it? Coal, yes, exactly. He's well acquainted with coal. I'm just teasing you, man. Don't worry about it. Huh? Yeah, there's coal right here, okay? That's an example of an organic sedimentary rock, okay? Why? Well, because it's made from plants, right? Yeah. You had your hand up? Oh, I thought you were going to ask a question. I was really excited. Okay. Coal is an organic sedimentary rock. Another example of an organic sedimentary rock, or a biochemical sedimentary rock, fossil limestone, okay? Comes from something that was once alive. All right, so when it comes to classic sedimentary rocks, we tell them apart by looking at their properties, just like with every other type of rock or mineral, okay? Properties for a clastic sedimentary rock include particle size, which is how large the grains are inside of my rock. Sorting, which is how many of them are approximately the same size, or is there a wide range of size in my rock? And shape of the grains. That's not shape of the rock. That's shape of the grains. Okay? The shape of the grain tells me what? Are my grains more angular or round? What information could that possibly give me?
How it was weathered.
How the rock was weathered, or?
The minerals were weathered.
Yeah, the grains, before they even became part of the rock, how much were they weathered? The more round they are, the more weathered those grains were before they became part of the rock, which can tell me something cool like how far that sediment came, right? How long did it travel before it was ultimately deposited there? Or how long was it swished and washed around in this place before it was ultimately deposited? All of these give us valuable information that we can interpret about environment. Okay? Chemical sedimentary rock, we've already talked about this. You've got your inorganic stuff, and then you've got your biochemical stuff. Now, fossils, like the ones that make fossil limestone, are technically rock. All fossils have become rock. That's what the process of fossilization is. Technically speaking, there is nothing organic about them anymore, but we kind of treat them as this weird middle ground because they originally came from something organic. Okay? Biochemical is a word that we can use to describe something in that weird middle ground, like a fossil limestone. Your truly organic sedimentary rocks, though, as far as you and I are concerned, just coal. Okay? Again, the accumulation of that plant matter. It gets squished down. It gets heated. It gets pressurized. It gets cooked. And the more it gets cooked and the more it gets pressurized, the more dense it becomes, the more nasty stuff gets removed from it, the more efficient it becomes as a potential energy source. You all know the difference between potential and kinetic energy? No, he just said kinetic is stored, and I'm saying to flip that. Potential is stored. I thought you said kinetic was stored. I'm sorry, I heard kinetic is stored. Okay, you corrected yourself. All right, I apologize. Okay, yeah, potential is stored energy. Kinetic is happening now energy, right? Good. This pen, experiencing kinetic energy as it falls. This pen right now, experiencing potential energy. In what way is this pen experiencing potential energy? Does this pen not have the potential to fall? That means it has the potential for energy in the form of gravity given to it by energy, okay, through acceleration. Potential now, kinetic now. Coal, oil, potential energy does not release energy unless we pull it out through combustion. We okay over there? He's crashing out. Huh? Wow. All right. Okay. Oil, all fossil fuels are potential energy sources. We have to combust them to release it. What about, say, radioactive isotope? Potential or kinetic energy? It's actually a nuclear energy. But as far as we're concerned, in these two, if we're putting it down in these two categories, we're going to call that kinetic. Okay? It is releasing energy ongoingly. Now, there's the potential for more energy if I split the atom, but it is releasing energy on a consistent basis already. Okay? A water wheel utilizes kinetic energy. Wind turbines utilize kinetic energy. Solar panels utilize kinetic energy. Fossil fuel, potential energy. Just want to make sure we get the difference straight here. Potential energy is very valuable to us because we can use it whenever we need to. We can store it until we need it. I have 5 gallons, of emergency gasoline in my garage if I ever need to get anywhere in a hurry and gas isn't available, right? That's potential energy I have stored. It's more difficult to store kinetic energy. What do we need to store kinetic energy? Hold on, wait. I want to ask this group over here. You guys know I like coming over here and asking you questions. Those are fantastic, by the way. Did you just make those?
No,
Those are cool. Okay. What are you asking? You need to use the restroom? Sure, yeah. Okay. What do we need if we want to store kinetic energy somewhere? Like, kinetic energy is happening, but I don't need it right now. I need something to keep it for later. What do we call that? Throw out a word. Somebody, please. Your laptop is currently plugged in, right? It is pulling energy into itself right now at this moment. But if you were nowhere near an outlet and you unplugged it, would it instantly shut off? No. It has energy stored in something. What do we call that? A battery. My friends, if we want to store kinetic energy, the only way we can is in a battery. Now, batteries can only hold so much energy, which is why we have to store potential energy as well. That's why fossil fuels are so important. If it was possible for us to store an indefinite amount of energy in a battery, my goodness, we'd already be living in a green world. We just simply absorb all of the wind and all the water and all of the geothermal and all the solar electricity possible and put it in this one battery that we can all access an infinite amount of energy from, and we'd be fine. Or at least we'd be well on our way. But batteries are finite, and the technology to develop them, the resources needed for that technology are also finite. Hence why we have this reliance on potential energy that we store for later, aka fossil fuels. Okay. Okay, so we can use our information, the knowledge we get from igneous and sedimentary rocks, to make some interpretations about the history of our planet. Okay? The environments that occurred and the things that lived in it from sedimentary rocks. Where tectonic activity took place, where coastlines were, the composition of our crust and mantle over time. That's stuff we can get from igneous rocks. We can make some very valuable interpretations about the history of our world with just these two types. But there's a third type. Before we move on to metamorphic rocks, any questions about sedimentary? Okay. Metamorphism happens as a result of the application of heat and pressure, but not too much heat. What happens if we heat up something too much? It melts. And what happens when we get melted rock? You get igneous rock. We've totally bypassed the whole metamorphic process. So we're heating things up, but not to the point of melting my minerals in my rock. At least not all of them. Okay? What are some of the sources of this heat, by the way? The Earth's core, proximity to the core, sure, sure. Volcanoes, yes. Pressure is a totally different factor that we will talk about in a minute. We're talking about heat for the moment. This heat, we'll talk about the other two sources that no one has said in just a moment, but this heat causes some changes to occur in my rock. Specifically, it's going to cause my ions to mobilize. That means that they are more willing to make new bonds. This is not melting, simply a change in the structure and mineralogy of my rock itself, as they are rearranging themselves to match what is stable in their new environment of high heat. Okay? The sources of these heat, geothermal gradient, which essentially is the closer you get to the core, the hotter it gets, right? About 25 degrees Celsius per kilometer of depth. Increasingly, it gets hotter, more metamorphism, okay? Then we said volcanism, right? Aaliyah, you said volcanism? Okay, rising magma, proximity to a heat source like a magma body, yes, okay? Then subduction is another one. When two plates collide and one goes underneath the other plate, there's friction there. That friction creates heat, and you can get a zone of metamorphism there at that contact. Then burial. Way out in the middle of a continent, nowhere near anything tectonic, what's happening? A heck of a lot of sediment deposition. Layer upon layer upon layer upon layer upon layer upon layer. We are living in a place where that happened. A basin, a low-lying area that got filled with sediment over time. Okay? The deeper parts of that are going to be deep enough that they get metamorphosed. Okay? Now, we talk about pressure. Autumn, you brought up pressure, right? Do you remember what the two types of pressure were? Under pressure. Doom, 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 doom. It's a good thing my videos aren't monetized, or I wouldn't be able to anymore, now that I've sung that. All right, should we shout out to the class? Should we phone a friend, aka everyone else? Give me one of them. Ask me, I know the answer. Wait, what was the question? That's great. What are the two types of pressure in metamorphism? Confining pressure? Differential stress. Boom, there they are. For confining pressure, That's the uniform pressure that you get from all directions when you have consistent pressure from everywhere. Okay? The same pressure that you feel at the bottom of the pool, pressing down on every surface of your body. Okay? That's confining pressure. In differential stress, that's where you have unequal forces of pressure. So you're getting more pressure from certain directions than others. Yeah. Yeah, sure. Okay? Sure. And so that's going to cause your layers of rock to fold, to bend, to undulate, to compact. Because they're getting shoved in these directions more than in others. And they're going to alter their shape and orientation to match it. Specifically, when directional stress is applied, in what direction does deformation take place relative to that direction of stress? Down relative to the direction of stress? What does that mean?
It goes to the direction of
It goes in the direction of stress?
It goes the opposite direction of the
Opposite the direction of stress, which is mathematical term for that is?
opposite way.
Huh? Perpendicular, right? Perpendicular to the direction of stress applied. If I were to bend this sheet of paper, it will bend up or down. If I apply stress from the left or right, layers of rock do the same thing. They are deforming perpendicular to the direction of stress applied. Okay? So because we know that, we can see how they've deformed. We can interpret the direction that the stress came from way back when. Another interpretation tool. So that's what happens on the large scale. That's what happens to my layers of rock. But what happens to the minerals themselves in my rock that is being deformed? If there is confining pressure, I mean, they recrystallize, usually larger, usually into different minerals. But what about in differential stress? We get a unique kind of texture called foliation. Foliation does the same thing under differential stress, but at the mineral scale instead of the layer of rock scale, where our layers of rock will fold perpendicular to the direction of stress applied. My minerals themselves will reorient themselves, recrystallize themselves, or flatten in the direction or opposite, in perpendicular to the direction of stress applied. Okay? This is called foliation. Reorientation, recrystallization, or flattening of minerals into a direction perpendicular to the direction of stress applied. Okay? Questions about metamorphism or metamorphic rocks? Okay. All right, now let's talk about resources for a minute. We've already mentioned some resources today. Name some of the resources we discussed today so far. Diamond, sure, yeah. What? Carbon, all right, yes. Well, atoms, it's like saying, hey, what was your favorite part of this book? The words, right? Atoms are part of everything. We talked about matter, yes, but that's not a resource because everything's made out of it. Huh? Coal is a resource. What else? Gold? Iron. I don't know that we talked about iron, but you're right. You're just going to make your way through the periodic table, guys? Cadmium. Well, all right, what else? Yeah. We did talk about uranium. That is a resource. No. We already talked about carbon. You already mentioned that. Let's get one more resource that we've talked about today. Anyone else have? Again, we're making our way through the periodic table. Let's come up with some other ideas. We already talked about someone already mentioned diamond. One more resource we talked about. He's throwing out all the keywords. I'm just going to flip through these. And you tell me, here, how about we hesitate over this real quick?
Carbon.
Sulfates.
Salt, sure. I'll take salt. That's a very common resource.
We didn't even talk about salt.
We did. We talked about salt.
I don't remember sea salt. Never the inorganic.
Yeah, we talked about salt as one of the inorganic mineral or rocks that we can get. All right. So those are all resources, among others, that we have discussed today and throughout 1403, that are required, absolutely necessary for our survival, for the continuation of our civilization and its progress. The unfortunate truth is, progress and greater population only requires more resources. More resources requires more mining, more drilling, and all of that. There are only two ways to solve this problem. Find more, or make the process more efficient as it currently stands. There's a lot of waste in the things that we do. If we can find ways to eliminate waste, all of a sudden that gives us more resources from the processes and the locations and the mines and the wells that we already have. That requires investment. And in the current economic philosophy of our world, or at least most places in our world, people would rather invest that money in new, convenient, easier sources. What's the problem with that? What's the problem with just going and getting something new all the time? You run out of new stuff. Okay? There's a finite amount of how much of this stuff we will actually be able to get, realistically speaking, which means that eventually we're going to reach the point where we have to invest in efficiency anyway. The smart move is to invest in efficiency while looking for a small amount of new resources. That's how you sustain it in the long run. The not so smart move, the short-sighted move is, oh man, I've run out of all the stuff I can easily get from this place. I'm going to dump that and go invest in a brand new place because I'll be able to make money faster. That's a good way to end up with a world pockmarked with deep mines and an economy that no longer has anything to support it because you don't have money to invest into efficiency when you get there. So it's a deep, not only physical, but philosophical problem in society. Not just with mining and the oil industry, but other places as well. And it's something that people are starting to pay more attention to. I have to put credit where credit is due. There is a lot of attention being put into efficiency right now, just not as much as is needed for it to become a more mainstream thought process. Hopefully we do get there before things get too far along, though, because we are burning our way through resources at an unsustainable rate. I mean, there's supposed to be 10 billion people on our planet in 25 more years, guys. Yeah, we're 8 billion, 300 or 400 million at this point, and it's only going to keep getting faster and faster as time goes on. Yeah.
I heard that statistic was wrong.
You heard what?
That they don't actually that they miscounted.
I mean, it's entirely possible they miscounted, but if I were to guess, I would say they miscounted on the low end. Wow. Well, so that's one of the factors. This number of this many people will be on this planet at this time assumes something like a world war won't happen. Yeah, that's for everyone on YouTube now. Congratulations. You just outed yourself as a Warmonger. Well done. Huh?
The entire world was like one big country, there would be no war.
If the entire world was one big country, there would be no war. You mean like you're talking about like a utopia where everyone is united? Man, that's my goal. That's my hope, right? I want everyone to be united behind something. My goal is to try and make policy that unites nations behind the efforts to get to the moon and share it, not fight over it. It would be wonderful if something like that was the starting point for something bigger, but at this point, that's just a dream. As far as the resources goes, though, resources are something that needs to be responsibly cared for, but we can't ignore the need of. Another possibility here is bringing resources from somewhere else, right? James Cameron. You guys know who James Cameron is? He made the Avatar movies. Blue people, the Na'vi. Who do you think James Cameron was? No, those are the Rousseau brothers. Oh, the guy that walked on the moon. No. 16 people have walked on the moon, if I'm not mistaken. Huh? The last time someone walked on the moon. Gosh, I don't remember the last year that someone walked on the moon. It was one of the last Apollo missions, I believe. But I don't remember the exact date. All right. I know that the space shuttles, the first space shuttle launch was 1981. And that was when they kind of turned their attention towards, let's focus on orbit, let's focus around Earth, and not so much putting people on the moon anymore. So it was sometime before that. What was I talking about? Oh, James Cameron. He's a film producer, makes the Avatar movies. He made the Titanic movie. He makes a lot of stuff, okay? Made one of the Alien movies too, I believe, which is cool. If you haven't seen the Alien movies, they're good. I like them. Huh? I don't know who made those. I don't think that was him. I don't think he made the Predator movies. But he actually, a while back, proposed this idea of investing into asteroid mining. So you go and you harness an asteroid, pull it close to Earth, and then mine materials off of that. So depending on the asteroid in question, you would be able to get a lot of stuff off of it. But there's a lot of math involved in making sure your asteroid doesn't become a problem, right? Smarter solution is park it around the moon, maybe, in a stable cislunar orbit around the moon, and then mine it there. And that might be something for sure, but most likely it would not be energy efficient to bring those resources back to Earth. That's probably something we would do to provide resources for facilities we have on the moon at that point. So there's a whole lot of conversation that goes into resources, but the biggest thing with resources right now is sharing them. How do we share resources to support everyone? That's a problem within nations. It's a problem within the world. There's not really any solution to it right now. I can't remember exactly where I was going with that original idea. We've gone off on like 3 tangents since I brought it up. I don't remember. Any questions about resources, though? No? Okay. Well, let's talk about your first lab then. Where is my... Turn this off real quick. All right. All right. So your first lab is going to be about sedimentary rocks and structures. Let me turn this back on. I'll just blow through this PowerPoint really quick with y'all. This is all stuff that we talked about in 1403. So your lab is going to be asking you to identify sedimentary rocks and structures because those are going to be relevant for the rest of the class. Okay? We're talking a lot about fossils. We're talking a lot about environments. Interpretations for things like environments and relevance for things like fossils comes from a study of the rocks that they were in, including any structures present there. Okay? So I'll just go through all of that. Okay, so common sedimentary rocks that you should remember through learning from 1403. Shale, fine-grained, thin-layered sedimentary rock. Smaller clay and silt-sized grains indicates that this formed in a very deep water or very calm environment. Not a whole lot of energy in the water that deposited it. Sandstones, medium-sized grains. Okay, so you get your usually made from quartz. These sandstones are usually made from quartz, but there are variations with high amounts of other things. Arkose, yeah.
What is that one on the right called?
Arkose. Yes. So this is called Arkose. It's high in feldspar content. It may even have larger pieces of feldspar in it, like you can see in this right there. Okay. Then you've got Greywacke, which is high in silt or clay-sized particles, as well as the sand-sized particles. So about 15% or more clay-sized particles, and you get a Greywacke. About 25% or more feldspar, and you get an Arkose. Arkose. Then you've got conglomerates. These are anything larger than the grain of sand, so 1 or 2 millimeters, I should say. Okay. So you can have two varieties of this. Okay. So you've got conglomerates, which we call conglomerates, where the grains inside are well rounded. Then you've got the type of conglomerate called a breccia, where instead of being rounded, the grains inside are very angular and sharp. These indicate high energy environments because it takes a lot of energy to pick up and move those types of those sizes of grains. And then the rounding of your particles in your rock indicate how far that sediment was transported before it was deposited, right? The rounder, the more weathered they were. You've got several varieties of limestones. You've got your inorganic limestones like micrite, which form through the precipitation of calcite in shallow seas. Same thing with oolitic limestone, precipitation of calcite in shallow seas, except those ones get rolled around until they make a sort of rounder shape before they get compressed. You've got fossil limestones, which are usually formed from the fossilization of reef systems. So crinoids, brachiopods, snails, all sorts of shells get broken up and smashed together and fused into a fossil limestone after that reef has been buried under sediment. Chalk is a type of limestone, but made from microfossils. So foraminiferans and planktons and things like that that died, fell to the bottom of the ocean and compressed into that limestone. You've got dolostone, which is just like limestone, but made out of dolomite instead. Doesn't react as strongly, does not have fossils, doesn't react as strongly to acid, I should say. Also does not contain fossils typically. Chert, which is microcrystalline microcrystalline quartz. So it's got the properties of quartz. It'll scratch glass. It'll do all that stuff that quartz will, except that it's made from tiny little crystals that coalesce together, precipitate out of some water solution, and makes these sort of geodes. That's what makes those. It can make random chunks of, we call them flint or jasper or chert nodules. Okay. But it will still have the properties of quartz. And then your evaporites like salt and gypsum. Your organic rocks, you've got coal. We already talked about coal today. Diagenesis is any change that occurs to your sediment after it's been deposited. This includes lithification, the process of becoming rock, through cementation and compaction. squeezing out the air and water between all your particles, and then some kind of cement, usually silica or iron oxide or calcite, forming a cement that keeps those grains together. Okay, so your sedimentary structures. Here are some of the more common ones you might come across. Bedding planes, indicating changes in the environment that sediment was being deposited in. Cross bedding, indicating different changes. These ones more physical, in this case, direction of whatever flow deposited that sediment. This can be true for wind if it's a desert, for water if it's like a beach setting. Okay, so if there's a directional change in that depositing medium, it will be there indicated by cross bedding. Graded bedding is what we see when we have, say, like a landslide above or in the water. So like on land or in the water, this will be true. When you have a landslide, there's a lot of energy, which means it's moving large, medium, and small particles at the same time. But as it reaches a less of an angle, a more gentle slope, what happens to my energy? It starts losing energy, which means I'm going to drop my large particles, and then my medium particles, and then my small particles pretty quick on top of each other. So graded bedding is whenever I see large, medium, small. And we'll often see them on top of each other, like especially out in the water where there's landslide after landslide after landslide off the edge of a continental shelf. We'll see large, medium, small, large, medium, small, large, medium, small. We call those graded bedding sequences. Ripple marks like this. We'll typically find those in places where shallow water was continually washing over sediment, fine-grained sediment. Okay, beaches, rivers, floodplains. Okay, mud cracks can be preserved in rock. We'll get these whenever water evaporates away, like a dry lake bed. Let's talk a little bit more about those ripples. There are two types of ripples. Asymmetrical ripples, where one side is steeper and one side is more gentle. And symmetrical ripples, where both sides are symmetrical to each other. What might do that?
Waves?
Waves doing what?
Like whenever like on a current, whenever like it comes down and then it comes back.
Ah, yes, the direction of flow. And an asymmetrical ripple is formed by one direction of flow. In this case, going that way, pushing this sediment into sort of this dune shape, going that one direction. With a symmetrical ripple, there is back and forth and back and forth. Where would we find symmetrical ripples? Where do we have flow that goes back and forth?
Coastlines?
Caused by?
The tidal waves hitting the coastline.
Waves. Tides, not really, because those are too long. The continual back and forth of a wave will make a symmetrical ripple, though. What about with an asymmetrical ripple? One direction of current. Where do we get that? Rivers. Deserts. Right? Good. Trace fossils. This is evidence of life without actually being a piece of that life itself. Footprints. Are these footprints part of a dinosaur? No, but they are evidence of that dinosaur, therefore a trace fossil. Burrows. Is this a piece of that animal? No, but it's where that animal lived, therefore evidence of that animal. These are trace fossils. Actual fossils are pieces of the organism itself, like these ones I've talked about before, pieces of dinosaur, pieces of turtle, pieces of tree. Okay? These are other different types of fossils right here. These are called stromatolites. Believe me, we will talk about stromatolites more in this class, but for now all you need to know is stromatolites are colonies of algae and sediment. What happens is a colony of algae grows in warm, shallow water. The tide goes out. Tide comes back in and brings with it a very thin layer of sediment and deposits that sediment on top of my algae. Algae requires the sun to photosynthesize energy, keep itself alive. So it grows above that little layer of sediment Tide goes out, comes back, does the same thing. So you get this algae sediment, algae sediment, algae sediment, algae sediment, and you go from a flat colony of algae to essentially what grows into a mushroom shape. And these are living stromatolites in Australia, by the way. Shark Bay, I believe this is called. But these are living stromatolites. The tide is out right now, obviously. Okay? And so they're exposed. These have been around in the fossil record for billions of years. The oldest evidence of life we have on Earth are stromatolites. Billions of years old. Okay? These are fossilized stromatolites. Okay? Something that you may confuse for stromatolites, but which are not, are called iron concretions. This is what happens when some obstruction, some piece of fossil, some piece of like maybe gravel or something, or maybe even just a void in a porous sandstone that water is moving through. Sandstone being a common example of this, okay? Water is moving through, and iron oxides and iron sulfides are going to collect around that object. That object essentially acts as a nucleus, and iron builds up around it into a weird sort of shape as time goes on. And that's where these iron oxides come from. They are not stromatolites. They may appear to be, but they are not, okay? You'll find these a lot where there's a lot of iron in your groundwater. The town in Washington State that my wife grew up in, there was an old dead volcano right next to it. They would go hike it all the time. And there's so much iron in the soil from this old volcano, from the volcanic rock that was weathering away, that the water in the sides of the gutters on the side of the street was red. And everybody's shower was stained red. Everyone's shower looked like a murder scene because no matter how many water softeners you put that water through, there was still some iron in it. Like there can be a lot of iron dissolved in water. You'd be surprised. Yeah. No, it is not healthy for your skin to go in that water raw. No. Okay. Any questions about your lab? No? All right, well then let's go ahead and move into lab time. We can work on it. I'm going to end the recording here. If any of my online students have any more questions, you can always email me.